Hello everyone, back on track number 2. So, who of you counted how many coffee machines they do have downstairs? Yeah? There another one? I counted 9. Why do they have 9 coffee machines? It's not just to provide enough coffee, it's also professional backup. What happens if one of these machines breaks down? Or imagine all of them break down at the same time. That would be a catastrophe for such a conference. So now we are in the middle of the next topic, predictive maintenance. It's probably the hottest topic for production industry. And I'm really happy that we have a top expert in this field today on stage. So please welcome Lilach Goren Huber. Lilach joined the University of Applied Science as a senior scientist in 2013, and she did a lot of statistics, machine learning, deep learning to prevent of exactly happening this, the breakdown of the machines. The floor is yours.
Thanks, Philip, for the nice introduction. So you did part of the job for me already, but I guess many of you know what is meant when we talk about predictive maintenance, at least more or less, or heard the terminology, the term, every once in a while. And also heard quite a bit about deep learning or artificial intelligence or machine learning. But today I would like to focus on something, on an aspect which is very relevant and quite specific, and to touch upon the gap between the research that is done in this field specifically of deep learning and AI for machines, for machine health, for predictive maintenance, and the state of the art in industry and application in industry. And to talk about this gap, using a couple of examples of how we could bridge this gap and bring in the beautiful and great tools of AI into application in commercial and in industry, in commercial applications. So let me take a step backwards and start with why we're doing it, even though you might already be familiar with that. With the coffee machine example, we're half the way there. So that's what happens when a wind turbine is really going crazy and going down the drain, and we want to avoid these kind of things, these kind of situations. We want to avoid long downtimes. We want to avoid loss of cost and risk to life. And how is it usually done? Nowadays, still in industry, mostly, with traditional approaches which are based on experience. Either reactive, we wait for something to happen and then address it, or preventive. If we cannot afford to wait because it's too risky or too expensive, we invest a lot of time, a lot of effort, and a lot of money in repeatedly checking up our machines and even repairing our machines in order to avoid a failure, a downtime somewhere in the future. Sometimes we make it, sometimes we don't, because we have no idea about the current situation, condition of the machine. So there comes data into play, and we all want to be able to use this wonderful resource that we have now for a while, which is data. And if we want to go from experience-based to data-driven methods, we are talking about condition-based maintenance or predictive maintenance. Condition-based maintenance is when we detect a problem in the machine, detect an anomaly, a situation which is a bit out of the order, and we address it in order to avoid a fault in the future. Predictive maintenance goes even a step further and tries not only to detect that something is going now wrong, but to predict when the machine is about to fail, such that we have a window to optimally plan our intervention. But let me tell you, most of the company, at least the ones I am talking to, most of the industry or infrastructures applications are not even up to the task of doing condition-based maintenance, not to mention predictive maintenance. So why is this? Why is condition-based maintenance still so rare in industry, even though research has been doing quite a lot of effort to develop methods, machine learning, deep learning methods, exactly for this purpose, to improve the condition of machines? And these two figures are supposed to encapsulate this gap between research and the mess we have in industry. So basically, this gap, what I think is one of the main reasons for this gap is because most of the advances that we saw in the last couple of years in AI were driven by industry. We know companies, big players like Apple and Google and Microsoft, that actually needed automatic text recognition, translation, virtual reality, what have you, very sophisticated methods based on deep learning, and they are driving these developments forwards. And when we come to the world of machines, we are in a different situation. Machines are traditional. Machines are there, most probably, in most cases, for years back, and they need a lot of domain knowledge. They need the engineers. They need the service technicians. They need the knowledge technical knowledge behind the machine. And there is usually a huge gap between people in charge of data, if there are any, in the company, and the people in charge of the machines, the engineers. And this gap has to somehow be bridged. And the acceptance of these new methods into implementing them in industry, is a stage that is still coming upon us. That's my feeling, and that's my perception, according to my experience with our partner companies. But luckily, in Switzerland, we have the financial mean called InnoSwiss, and that enables, to a large extent, going in the direction of bridging this gap between research and industry, and that's what I'm going to tell you about today, how we did that in a specific case together with our partner, Nispera, in an InnoSwiss project whose target was to develop a predictive maintenance toolbox, software toolbox for the owners and operators of wind turbines. Nispera is a very unique case of a very innovative small startup that is actually no longer a startup, maybe because of that, and was bought by a bigger player in this field of energy called Fluence. And they became aware of the fact that their clients, the owners of wind turbines, have the data already on their part. They have historical data, a lot of historical data, maybe not the highest quality data, maybe not the highest resolution data, but this data is coming from a SCADA system, a supervisory and control system, installed on the turbines in a standard way from day one, usually, of the installation of the turbine, and it's not being used for condition monitoring and predictive maintenance yet, in an automatic way. And that was the goal of this project. So the question is clear. We want to detect faults early enough such that we can warn the technicians and send technicians in time, plan maintenance interventions such that we can do it efficiently with short downtimes, as short downtimes as possible. So we have to tell a machine, a turbine which is healthy from a turbine which is faulty, which has a problem. So why don't we just go back to the known problem and treat it as usually the AI is treating the problem of telling spam mail from normal mail, and just give the machine learning or the AI a lot of examples of regular mail and spam mail, and ask it to classify into the inbox or into the spam folder. That's how it works with emails, and it works quite well. But now when we go to the world of machine, how would it work? We have to show the classifier, the AI, we have to show it a lot of examples of a healthy machine and a lot of examples of a faulty machine, and teach it to tell between the two. But this is not the way it really works, because in real life, we almost don't have data of faulty machines. We want our machines to actually function. So the approach in this case is pretty standard. It's called anomaly detection. It means that we teach our AI based on healthy data only, without showing it any faults, and teach it to predict the healthy condition of our machines, of our turbines in this case, And once it's exposed to real data online, it can tell, this example is not what I know. It's different from everything I've seen in the past. It's different from everything I was trained on in the past, and detect it as an anomaly. So that's actually what we did. Also in this case, for the wind turbines, we showed our AI examples of sensor data from wind turbines, from a wind turbine in this case, which is, corresponds to the measured power of the turbine, wind speed, the temperature of the surrounding, and, for example, the temperature of the generator bearing. And we taught it, we trained the AI with normal data only. We trained it to be able to predict how the temperature of a certain component, for example, the generator bearing temperature, should look like for a healthy machine. And then in real time, when deploying this algorithm, we asked it, what does the AI expect from a normal behaving turbine? What should be this temperature? And compared it with the red line. The red line is the measured, the real actual measured temperature. And when we saw, when the machine learning or the AI detected strong deviations, it set up an alarm automatically. And that turned out to work really well for the generator bearing temperature of a turbine. And that's one example which is from real life, real data. In this case, what you see here in the red line starts deviating around 6 weeks before the machine itself was shut down. So if we could have deployed this in real time, we would have had 6 weeks to plan ahead the maintenance, which is quite okay. So it works quite well, but I'm hiding something here. And one thing I'm hiding is, I told you that we need historical data, we need healthy data to train this algorithm. And one question is, who tells us which data to take? Which data is healthy if we haven't done the anomaly detection yet? That's the problem of unsupervised anomaly detection. And to go fully unsupervised, we had to develop specifically an algorithm. Usually this problem is not tackled by research. It's not something that you find in many papers, in many scientific papers. That's the upper part. But in real life, you have to tackle this problem. In real life, you have to make sure that your whole data pipeline is automized. The whole process is automized from the beginning to the end. And that includes also selecting the appropriate training data. And that's what we developed in this case for the wind turbines, an algorithm that is based on AI and is selecting the appropriate data in an automatic way and enables the whole pipeline to be automatic without manual intervention. So now that we're happy about what we did with one component, the generator bearing temperature, are we done? The question is, the answer is, of course, we're not done, because as opposed to research where we can allow ourselves to focus on a specific component, in industry we have complex systems. A turbine is a complex system. It includes many components, and for each one of them we would have to train such an AI algorithm, and that would be a disaster. In terms of computation and in terms of development and maintenance of the code. So is this really what we have to do? And the answer is no in this case. And now I exaggerated. So we realized that if we use a convolutional neural network, in order to do the anomaly detection, we can actually scale it up quite easily and make it predict, instead of just one output variable, instead of just one component temperature, we can make it predict 10 or 30 different variables as an output with the same computational effort and with almost the same accuracy as for one component. This is definitely a sacrifice that is worth taking if you want to scale up your algorithm to such a complex system. So what you see here in this plot with blue and red are the health indicators or anomaly scores. It basically indicates whether the specific component on the panel is healthy or not. This is over a period of 2 years, and if it's healthy, you see blue points, and if it's deviating from healthy condition, you see the red points. And so in this way, you can get a picture of your whole complex system and each component with its own health indicator, and you could go one step further beyond just detecting that something goes wrong, also knowing where actually something went wrong and where not. And that's diagnosis already. So that's the next step, and that's a generalization which is rarely done in research but is essential for industry. Another step towards scaling it up is asking the question, okay, now we did it for one machine, what about the whole fleet of machines? In this case, what about the whole park of turbines? Or the same company usually owns several parks in different places over the world with different climate conditions, with different models of machines, with different operating conditions. How do we generalize this? How do we scale it up? Again, a problem that research usually doesn't tackle, but industry needs. In this case, our method was to scale it up using transfer learning. And transfer learning is a method which is known in the field of AI, usually in deep learning, and is used in order to train on one instance and actually deploy the model on other instances, transfer the knowledge to other units. In this case, training on one turbine and transferring the information, transferring the ability to predict to all other units, all other turbines in the park. This transfer learning is not just trivially done. It requires an algorithm that does the transfer, and in this case, we realized it needs a designated algorithm that does the transfer, that fits to this system, that fits to the turbines, cannot be just taken off the shelf. The message you should take from these complicated plots is a comparison. What happens when you use transfer learning on the left side, and as opposed to what happens if you don't use transfer learning and you just train from scratch each and every unit in a very inefficient way, especially if you have a park of hundreds of turbines. So what you see here is that the plots look very similar. So using transfer learning, scaling up your computation for a whole park, or even beyond the same park, works very well. So by now I've told you about several aspects, several challenges that we had to tackle because we wanted to deploy the algorithms for Nispera in a real commercial system that are usually not addressed. Where should I? Stopped reacting. Hello? Is there some intelligence here that can do magic and move one slide forward for me? It doesn't work anymore. Anyway, I told you about several aspects in which we see gaps between research and the state of the art that is deployed at the moment in commercial systems, in industry. That requires challenging our algorithms, taking them a step further. And another one of these steps further that we want to take our algorithms is to ask the question, what happens when we have limited data, when we don't have as much data as we would like to have, as we would need in order to train our algorithms in an efficient way. For wind turbines, you don't see the slides, unfortunately, but for wind turbines, there's really no way that I can make this thing move. Technology, wonderful. Okay. This doesn't move. Okay. So if you could see, you would have seen that that one of the problems in having too little data is having biased data. Actually, in the case of wind turbines, it's very clear that if you train your your automatic detection algorithms, your automatic predictive maintenance algorithms on data from winter, you can't expect them to work well in summer, where conditions, the ambient conditions are completely different. And this is exactly what happens. If we have a new fleet of machines, a new park, and we want to start deploying the algorithms on a new park with data of 1, 2, or 3 months, we want to start deploying right away. So one way to do it is take data from another park and use transfer learning, and this we do as well. We implemented that as well. Another approach is to realize that you actually have a park with tens or even hundreds of machines. Oh, it's getting better. With tens or even hundreds of machines, and to combine the information from all of the park in order to boost up your knowledge. So you have short time, but you have a lot of machines. You can combine this information. In this case, we combined a bunch of convolutional neural networks for each one of the machines. We combined the information of those in a way that allows us to get over a problem of false alarms that showed up in summer. So the result of not being able to train with summer data in this case was having false alarms in summer, having a situation that the AI never encountered in the past and was interpreted as an anomaly. And with using data which was over the whole farm, over the whole wind park, we could get over these false alarms, avoid these false alarms, but still detect the real true faults that appeared later on. So that would be wrapping up a couple of examples that were supposed to be were supposed to show you how wonderful a miracle happened. So that's the solution for limited data, which I already told you about. Can we go one further? Great. These are the false alarms. Can we go one further? One more. Right? These are without false alarms when you integrate the data from the entire park. Now we can go one further. Sorry for this. Can we go one? Okay, so I'm done, basically. And I hope you take the message that we need to bridge a gap between research and industry when it comes to real technical machines. We can bridge the gap. I see it as partially our role at the Fachhochschule, the University for Applied Sciences, to bridge this gap. And if you're interested in more details about these examples of how we actually technically bridge the gap, you have here some references for this. And if you're really interested in what I told you about, then consider scanning this and joining us.
A top expert, not just in predictive maintenance, an expert as well in improvisation. Thank you, Lila. Sorry for the problem. We have time, a little bit less, but if there are questions in the audience, just raise your hand. There is one.
Very top.
Yeah, run.
Can you just bridge the gap?
Maybe you can quickly elaborate. What's the status right now? Is it up and running? Is it hot out there in the field?
This is up and running for a while now, yeah. This is up and running, first version already a year ago, and keeping up with our research, we update the versions all the time.
The neural networks run in the cloud or on each wind turbine itself?
In the cloud.
All in the cloud?
The networks in the cloud, because the data is anyway streaming to the cloud at Nispera's side, now Fluence. So on their side, they anyway stream up all the data, and they gather all the data, but they can choose, of course, the training data then from one turbine or from a couple of turbines and wherever, and then train it on the cloud, yes. Mm-hmm.
Hopefully it was not the answer to your question.
It wasn't. Thank you very much for sharing your research. I have a question regarding the prediction errors. These are used as a health index for the turbines. Where how do you come up with the threshold? When is the prediction error high enough to classify as an anomaly?
So I could actually, no, I cannot. One of the points, this is a great point that you raised, because it's exactly a point that is never discussed in scientific papers, or almost never discussed. It's hidden. It's, and this is a point we also elaborated on, how to actually automize the threshold setting. And it does require eventually a parameter. But what we did is we set this parameter to have a meaning, a statistical meaning, such that the client can translate, can decide on how to set the threshold, because it's always a trade-off between how reliably I detect and how many false positives I have, how many false alarms I have, right? It's always a trade-off, so we have to set the threshold somewhere. But if you can communicate to each client what it means in terms of how many alarms are you going to miss if you set the threshold here, then the client can decide where they want to set the threshold. In principle, it's always set based on the training information, right? You have your training data, you have a distribution of errors from the training data, you can set the threshold at the tail of this distribution, right? This is trivial, but where exactly at the tail of the distribution you set it is still a parameter that has to be fixed according to the client's requests.
Thank you.
So I have to finish here. Thank you very much again, Lila.
Welcome.
You get the golden bottle. Hopefully you'll
Thank
find
you.
your name on it. Thank you, Lila.